Next, we will look at the concept of regular languages. And to define a regular language, we need to define the concept of a regular expression on an alphabet sigma, and it's defined recursively. The empty set is a regular expression, and you can take the clean star of the empty set, which is equal to itself. And the empty string by itself, lambda, is a regular expression. And for all x, for all symbols in this alphabet, x, just one of the symbols, is a regular expression. And if A is a regular expression, A here can represent either a string or a set of strings. Then A star, its clean closure, is also a regular expression. For instance, you see, if your alphabet is the binary alphabet, 0, 1, then this will be a regular expression. If A and B are regular expressions, again here A and B can be symbols or strings or sets of strings. If they are regular expressions, then AB, the concatenation of A and B, is a regular expression. Now, the concatenation, if A and B are strings, is trivial. And by strings, I also include the symbols because symbols are just strings of length 1. But if A and B are sets, then think of this as a version of a Cartesian product. For instance, if A is the set 0, 1, B is the set 0, 0, 1, 1, then A concatenation B will be pairwise concatenation. So 0, 0, 0, 0, 1, 1, 1, 0, 0, and 1, 1, 1. This is how you obtain the concatenation of two sets in this context. And then if A and B are regular expressions, again, A and B here can be strings or sets of strings. And then A plus B is a regular expression, and plus here actually indicates a set union. So sometimes you see, for instance, Rosen uses this notation, union, and in some resources you can see this strike notation. But this is essentially a set union. For instance, again, if A and B are defined in this way, then A plus B is going to be 0, 1, 0, 0, 1, 1. Simple set union. So this is how you can come up with a regular expression. And a regular language is a language that can be defined by a regular expression. So the set of strings that conform to this given regular expression. And Klein's theorem states that a language is a regular language if and only if there is a finite automaton recognizing it. This is an extremely important and powerful result, and it defines a class of formal languages called regular languages. I'm not going to give you the proof of this. It's not that complicated, but it takes a little bit time. If you're interested, you can read this on Rosen's book. But the implication is significant. If you can come up with a regular expression to represent the description of a set of strings, then there definitely exists a finite automaton that recognizes that language. Here are some examples to regular expressions, and all of them are regular languages. So 1, 0, star. So here, if you do not have any symbol in between, you should understand a concatenation. And the clean star applies to, if no parentheses are used, the clean star applies to the symbol. So 1, 0, star is a 1 followed by any number of zeros. So it could be 1 followed by 0 zeros, or just 1 0, or 2 zeros, or 3 zeros, and so on. This is a regular language. So it's the set of strings that start with a 1 and continues with a number of zeros, however many. And this one is different because now the clean star is applied to not just the symbol 0, but the string 1, 0. So this is any number of copies of 1, 0. And the empty string is involved here. It's not in the first one because you just need the first one. Here, the empty string, and then just one copy of 10, 2 copies of 10, 3 copies of 10, 4 copies of 10, and so forth. Okay, and 0 plus 0, 1. Now this is just the set 0 and 0, 1, because you see this one indicates union. So you are essentially saying this one or this one. So the string 0 or the string 0, 1. Next one, you see 0 plus 1 means either of 0 or 1. And a clean star gives you any possible string. So what is significant here is the beginning 0. So any string beginning with 0. 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, and so on. Any string starting with 0 defines this regular language. And the next one, 0 star 1 star. Any string not ending with 0. So how do we see this? Now you have any number of zeros here, followed by a 1, and this pattern is repeated as many times as you like. So the empty string is included in this one, this regular language, and then you might have any number of zeros followed by a 1, and this pattern can be repeated as many as you like. You can have another one here, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 1. But you need to have a 1 at the end, and so that your string doesn't end with 0 due to this 1 here. Now this one, this is interesting. 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 star. So you see, this is the strings consisting of well, a number of repetitions of one of these 4. So it could be the empty string. It could be either one of these, 0, 0, 0, 1, 1, 0, 1, 1. Or it could be 2 copies. For instance, you choose 0, 0, and then 1, 0. You can choose 1, 1, and then 0, 0, 1, 0, 0, 1, etc. You see, however many copies you use, the string you obtain is going to have a length which is a multiple of 2. So this is the set of strings with an even length. For instance, you can define set of strings with odd length by adding just another here. Or let's look at the other one, 0 plus 1, 0 star, 0 plus 1, 0. And these are the strings ending with a 0 and not containing 1, 1, because you see we are not letting 2 1s come together. And the string will end indefinitely as 0 because each of the possible endings are zeros. So it's not going to be end with a 1, and no 2 1s are going to appear together. And finally, strings containing an odd number of zeros. So to have an odd number of zeros, you need to have at least 1. So this part guarantees that. You can start with as many as 1s as you like. We are not interested in the number of 1s. And then you have a 0, and you can follow this by as many 1s as you like. Remember, star also includes 0. So the 1 star is lambda 1, 1, 1, 1, 1, 1, etc. And then you get a 0, and then again 1 star. So you see, I have a bunch of 1s, but among them, I have exactly 1 0. And this one is, again, the set of strings with an even number of zeros, because you see, I have a 0 here, followed by a bunch of 1s, possibly none, but maybe multiple, I don't care. And I have another 0, followed by possibly a bunch of 1s. And this is repeated due to this clean star. So anything I have in this portion of this string is going to have an even number of zeros. And when I concatenate that with this part, in total, I'm going to have an odd number of zeros.